Before starting CAN communication, let us understand what a network is and how networks are configured in a vehicle. A network is a system of digital connections. This is an exchange of information between devices or people, which happen over computers or social networks in everyday life. In other words, a network means connections that allow systematic communications between people. A vehicle network plays a highly important role in cars. It ensures the very basic functions of a car to accelerate and brake as intended. It also determines the perceived reliability of a car and technologies it features. Let's have a closer look into network and data communications using the example of FCA, short for Forward Collision Avoidance Assist. The camera and radar systems detect danger in front of the car, but they do not apply the braking force to avoid it. So, they use a network to communicate with the ESC module about the danger, and the ESC promptly applies hydraulic pressure to brake the car. At the same time, the information about emergency braking is shared on the network and communicated to the driver on the cluster display. The series of controls is based on organic communications between modules. Take another example. You may not think too much of the vehicle speed you see on the cluster, but speed is an essential data that concerns all control units. This is a sensor signal used by different systems to perform various actions, such as gear change by the automatic transmission system and front-rear torque distribution by the AWD system. This signal also is used to recognize the risk at the speed and determine what action is required. Then, why not connecting all controllers directly to the speed sensor? Doing so will dramatically increase wiring and the weight of the car as a result. Complex wiring also means an increased risk of faults from poor connection or disconnection. Consider this configuration instead. The speed sensor is connected to the ESC module only, which shares the speed data with other controllers through a shared network. This signal is delivered to the engine and transmission through the network, while other units can simply ignore the signal as they do not need the data. This is how information is shared through the network. In vehicles, the CAN communication is typically used for this purpose. An important requirement to enable such communications between controllers is a common language. In vehicle network, this language is called a protocol. The speed of communication, which means data transmission rates, should also be consistent. The CAN communication is one of such communications protocols. CAN is also at the heart of vehicle network technology today. The protocol is defined by Society of Automotive Engineers Standard SAE J1939. The configuration is quite simple. Controllers send their data to a network of two communication lines to share information. Connecting a diagnostic device to this network allows for accurate inspection and calibration of all connected controllers quickly. There are various ways to configure a network. In a star network, every controller is connected to a central hub. despite some benefits it may offer. The problem is that the main unit is heavily loaded, so the entire network is down if the hub fails. Whereas a bus network is commonly used in vehicles. Each bus forms an independent network. It is easy to add, change, and remove controllers to a bus. Bus networks are simpler in structure, which is another advantage. Vehicle networks are referred to as CAN bus network, as vehicles follow the CAN protocol. Now that we have covered the meaning of network and its benefits, let's move on and talk about the types of vehicle communication. K-line is a serial network protocol for diagnostic communication mostly used in the past. LIN allows for local communications between the master and slave components. Another protocol that is most commonly used in vehicles is the CAN communication, offering speed as an advantage. Note that KWP 2000, which is a keyword protocol for vehicular diagnostics, is similar to K-line, but KWP 2000 is faster, and its data frame structure is slightly different. Let's take a closer look at each. First off, K-line. This communication is rarely used today. This was used for one-way communications to check the system for faults. The characteristic of signals found in the waveform shows that the controller supplies approximately 12-volt power to the diagnostic device through the OBD connector. The diagnostic device drops this voltage to the ground. In this case, the controller recognizes there has been a change in the output voltage and understands this is an attempt by the diagnostic device to communicate. This is the real-world waveform. The input voltage from the controller to the diagnostic device constantly changes in patterns. Waveform analysis is a complicated process and not commonly practiced in the field. But we will take a quick look to understand how the system works. The diagnostic device changes the 12-volt power to the ground once. This is a wake-up signal to initiate communication with the controller. The powertrain or a relevant system confirms the communication line is available and the controller responds. Then, the diagnostic device and the controller can start diagnostic communication. The process of the data request and controller responding is repeated. You can see the data request is made and responded by the controller. This request-response communication is through single-wire communication, which is the way K-line works. As mentioned earlier, KWP 2000 also uses this type of communication. LIN communication is mainly used to complement CAN communication. The L stands for local. The most characteristic about this network is the configuration of master and slave components. Slave components are actuators and sensors, operating based on the signals from the master. Take an example of parking distance warning. When reverse parking, the body controller requests ultrasonic sensors for information regarding any objects behind the vehicle and receives the data from the sensors. This is also request-response communication. This uses a single wire. The characteristic signals are also similar to K-line. The CAN communication, the most representative vehicle network, is Controlled Area Network. Unlike LIN communication, every controller in this network works as a master, sharing the two bus line wires. The controller connection is also based on two wires. Look at the controllers that are connected to a shared network line. The engine ECU, for instance, transmits information such as RPM and accelerator opening. Likewise, all the information from other controllers is shared via this network. This way, controllers can get the information they need and respond to the request from each other. If wheels slip on an icy road and the ESC sends a signal, AWD distributes traction to the front and rear wheels, while the engine ECU reduces torque to allow the car to get rough driving performance, all in an organic manner. Notice each of the two lines generates their own waveform. It may not be easy to determine the normal waveforms from abnormal waveforms. This is because it is measured at a low sampling speed. Still, there is one clear pattern. Two waveforms have the opposite shape as if they are mirror images. Let's take a closer look. One goes up from the base 2.5 volt to 3.5 volt. The other goes down from the 2.5 volt to 1.5 volt. The upper waveform is from what we call CAN high, and the other from CAN low. In communications, CAN high is referred to as bus A, and CAN low as bus B. The contrasting waveforms from the high and low lines represent the language of binary digits 0 and 1. Let's go over the binary numeral system that uses voltage signals. Look at the high signal going up to 3.5 volt, and in the low signal going down 1.5 volt. There are parts where both high and low lines are at 2.5 volt. There is no voltage difference. This part is recessive, which is 1 in binary numeral system. Now, look at the part where the voltage goes up to 3.5 volt in high and down to 1.5 volt in low. There is about 2 volt difference between the lines. This part is dominant and is represented by 0. The combination of 0 and 1 is the language in which various forms of information is communicated that cars operate based on. This is the CAN communication voltage algorithm. In the comparing circuit A, there is no difference in the phase input, showing the same amplitude. Here, the output is 0 volt. Look at the circuit B below, with the 180-degree opposite phase input. The output voltage is twice the amplitude. This is the principle of CAN communication. It receives a pair of the 180-degree opposite input voltages and reads data from the voltage difference between the two signals. Even if noise in the CAN line affects both wires, the phase is same on both wires, which makes CAN more noise resistant. Binary codes are found in our daily life, such as barcodes. A barcode scanner generates light to read the code. The white part that reflects the light reads as 0, and the dark part that absorbs the light reads as 1. These bars of various thickness represent a code made of binary digits 0 and 1. Note the similarity between the barcode and CAN communication waveforms. The high and low voltages in the CAN communication are converted into the binary language of 0 and 1, and this is how the message is understood. CAN communications require something called a data frame. The communication does not only sends data, but also receives data from other controllers. And there has to be a standard set of rules to follow for transmitting and sharing data without error. The data frame is a structure that allows the transmission. To help you understand, let's imagine a meeting. The engine ECU transmits the start of frame bit, which is a request for the right to speak. When permitted, the ECU introduces itself, offering its ID, and transmit the data to the CAN bus. The data includes the RPM and APS opening. It continues to transmit the data for a set period. Then, it receives confirmation from other controllers that they all got the information. Then, ends the speech. For this to happen, the speech must be done in a common language at a constant speed. This set of rules is called a protocol. Click on the tip to learn more about data frame terminology. We learned that the CAN communication is capable of processing a large amount of data at a high speed. While the speed is an advantage, the number of controllers equipped in a vehicle is increasing dramatically, and connecting all the connectors to one CAN bus will be overwhelming. Imagine heavy traffic in a single-lane road. To prevent this, CAN communications are grouped into high-speed and low-speed CAN. Powertrain and safety systems are connected to high-speed CAN, while multimedia and convenience systems are connected to low-speed CAN. This helps distribute the load and also better efficiency. Low-speed CAN is also known as fault-tolerance CAN, for the special advantage that communication fault in one controller does not affect other controllers in the group. In addition to the speed-based classification, the vehicle CAN communications are grouped by subsystems, such as PCAN, CCAN, BCAN, and MCAN. High-speed CAN communications include PCAN, that is powertrain CAN, to which powertrain and drivetrain controllers such as the engine, transmission, and four-wheel drive. CCAN, that is chassis CAN, is used to control brakes, ADAS, and the cluster. DCAN, with D standing for diagnosis, allows for communications between each controller and a diagnostic device in vehicles with a central gateway. Low-speed CAN group includes BCAN, that has body controllers only, and MCAN, responsible for communications between multimedia controllers such as video, audio, and head-up display. ICAN is a high-speed CAN line dedicated for secured communications between the gateway and AVN to protect the vehicle and personal information over wireless networking. Let's take a closer look at low-speed CAN. The output signals are similar to high-speed CAN we just learned about in terms of digital signal characteristics, except the voltage signal level. Low-speed CAN consists of a high line with voltage going up from 0 to 3.5 volt and a low line going down from 5 to 1.5 volt. The data is coded in binary digits, where sections with 5-volt difference between the lines, 5-volt and 0-volt, are recognized as recessive 1 sections with 3.5-volt and 1.5-volt. 2-volt difference between the lines, in other words, are dominant 0. Transmission speed is another way to distinguish high-speed and low-speed CAN. Typically, high-speed CAN is used for powertrain chassis systems. While it supports up to 1 megabit per sec, 500 kilobits per sec is normally used in the vehicle. Low-speed CAN, on the other hand, is mostly used for systems such as body and multimedia. While it supports up to 125 kilobits per sec, 100 kilobits per sec is normally used in the vehicle. Connecting controllers to high-speed and low-speed CAN for the transmission rates they require helps distribute the load and allows for effective data processing. CAN communication requires 2 wires, high and low. When you look at the wires, you will notice that conductors are twisted together. This is also marked in the ETM schematic. This is called twisted pair wire. Twisted pair wires are noise resistant. The contrasting signals used by the high and low lines in CAN mean that the magnetic field on each line is also in the opposite direction if the current flows in the opposite direction. Twisted conductors prevent magnetic interference. In other words, the lines offset each other. Since both lines are equally affected by the noise, the impact of noise can be removed in the way a differential amplifier works. In addition to the twisted pair wire, the CAN communication also features 2 resistance points called terminating resistors. What do terminating resistors do? Voltage signals generally travel along the wires, gradually weakening, but reflected at an end of the wire. It is important to prevent the reflection, especially in CAN, where high-frequency communications are processed. Placing the terminating resistor of 120 ohm at wire ends ensures constant current flow, reducing the signal reflection and making the network more noise resistant. Without terminating resistors, there will be abnormal signals present in the CAN bus lines. If a controller is connected without terminating resistors, signals are sent to the CAN bus in the shape of a gear, which can overlap the normal signals and cause a communications error. The location of terminating resistors varies depending on the communications group. In PCAN, the 120 ohm resistors are found in the gateway and the engine ECU. In CCAN, they are in the gateway and cluster, while BCAN has them in the gateway and BCM. We do not see terminating resistors of MCAN for multimedia in the diagram. This is intended for head-up display, audio, video, and amplifier that do not require high-speed processing. For this reason, MCAN is low-speed CAN, and the terminating resistors are inside units, 2 for each, and not on the wires. This means an internal resistance failure in one unit or a unit with communications error does not affect other systems or the CAN bus. More recently released cars are now equipped with the central gateway, a module that is directly connected to BCAN, PCAN, MCAN, and the likes for organic information sharing between networks based on the transmission rate and data size. DCAN is added to meet the ever-tightening security standards, intended specifically for diagnostic device connection. It offers increased security with data encryption. Local CAN is used by systems where fast information sharing is most important, such as FCA and LKA. It is high-speed CAN to which only the relevant units are connected. The diagram indicates that, in addition to FCA and LKA, BCW also communicates with the rear corner radars via local CAN. We have learned about the CAN communications so far. Vehicle network technology leads to the future of the automobile industry. It is the key to implementing self-driving cars and connected cars. It is the technology that ensures all the cars on roads today function fully as they are intended. Thank you for joining and completing the overview session. CAN communication is connected to numerous controllers via complex wiring, and the accurate diagnostic approach is important. In this session, we are going through 3 topics, covering each in details. Firstly, we will learn what communication-related DTCs mean and what causes communication error with the diagnostic device. Secondly, we will complete the topology based on the circuit diagram and analyze it. Lastly, we will use the 120 ohm terminating resistors to locate an open and short circuit in wires. The most common DTCs related to CAN is bus off, timeout, and message error. The 2 CAN lines and the data frame resemble a train traveling on a 2-line track. Remember this analogy as it will help you understand the concept. First, bus-off DTC is generated when the transmitting unit is unable to send data to the CAN line. This is when either of the 2 CAN lines is faulty. In our analogy, the train cannot continue to move along the track. So, bus off means no data transmission. How does a controller detect bus off then? Look at the data frame and notice the ACK bit at the end. This is the signal from a receiving unit, not the transmitting unit, confirming successful data transmission. If the transmitting unit does not receive this ACK bit, it determines the data it sent was not received by the other unit and generates the bus off DTC. Remember, bus off is a DTC only detected by a transmitting unit. For instance, this DTC will be generated if the engine ECU is in bus off state, which means it is unable to transmit. The TCU, ESC, EPB, and MDPS that share and require data from the ECU will generate timeout instead of bus off. Timeout means that they waited for the data and it did not arrive from the engine ECU. Timeout is generated by a receiving unit when it does not have data transmitted through the CAN line. This could be the situation where you are waiting for a train and seeing only other trains are arriving. If the engine ECU has a problem transmitting data, other controllers cannot have the engine information they need. After waiting for a set period, they will generate timeout. These are all referred to as EMS timeout. So, this DTC indicates that the ECU needs to be checked or there is a disconnection somewhere in the related sublines. Message error is a DTC generated when the received data is invalid. It is detected only by the controllers that require that specific data, not by the transmitting controller. Back to the analogy. This is when you discover that the train in your platform is not your train. In the list of DTC guide, ESC generates message error that signals from the EMS, EPB, or MDPS are invalid. MDPS also have DTCs to indicate invalid CAN messages from other controllers such as EMS and ESC. Message error can be caused by a fault in the transmitting unit, data corruption due to reasons not originated from CAN, or sensor and actuator fault related to the message. Among the several causes for communication errors, let's look at the main and subline problems in the CAN bus. If the main line of the TCU has a problem, it won't be able to communicate while other controllers can. Inspecting the entire CAN line with all the wiring is difficult, but there is a trick. The OBD connector is located inside the car and also in the engine compartment, so you can check by connecting from each location. If there is indeed a problem in the TCU main line, the unit will be unable to communicate from both connectors. This indicates that the problem is with the TCU itself, narrowing down the scope for inspection. Also note that other controllers will generate a TCU timeout DTC in this case. Now, let's move on to the next example where both main lines of the CAN bus are disconnected. Here, only the ESC and cluster are unresponsive to diagnostic communication, while other controllers respond normally. In this example, ESC and the cluster can still communicate with each other, even if the main lines are disconnected, as long as they are connected normally to the CAN bus, and one terminating resistor is enough for transmissions to go through. If a CAN bus main line is shorted to the body, on the other hand, all data on the line is lost, and the entire system will be unable to communicate. In this case, continue checking while removing intermediate connectors on the CAN bus one by one. Here, the ECU, TCU, and ACU can communicate from the engine compartment, while connector A is removed. All other controllers cannot communicate through the interior connector. Now, removing connector B. From the 20-pin connector in the engine compartment, the ECU, TCU, ACU, 4WD, and MDPS can communicate now. From the interior connector, however, ESC and the cluster are still unable to communicate. Diagnosing the problem by removing intermediate connectors help narrow down the problem. The CAN bus is the connection of all controllers in the entire vehicle. The CAN bus is the connection of all controllers in the entire vehicle in a highly complex layout. This is why visualizing the layout by drawing a simplified diagram is necessary. Having a topology diagram of CAN allows you to identify each controller connected to the interior and engine compartment connectors. It also helps you remember the location of the intermediate connectors as you remove them. Vehicles with this central gateway have a discrete network, which means inspection must be performed at the group level of PCAN, BCAN, MCAN, and so on, confirming that the problem is only with the powertrain controllers or certain controllers in a network makes easy for you to narrow down the cause. Here, we are going to learn how to diagnose the problem by measuring the resistance. When the entire wiring and both the terminating resistors are in the normal state, the combined resistance of the CAN bus should be 60 ohm. If either of the CAN bus lines is disconnected, it no longer forms the parallel circuit, and the resistance will measure 120 ohm. This is also the case when both lines are disconnected. If there is a disconnection in a subline to the controller, not the main lines, the CAN bus resistance will measure 60 ohm. This is also the normal resistance value. In this case, however, the controller is unable to communicate. In this case, you need to measure resistance in the sublines. If the subline resistance is 60 ohm, this means the wiring to the main lines is in the normal state. If there is a section where the resistance of the unit itself is measured instead of 60 ohm, this indicates a disconnection somewhere in between the two lines. Let's discuss the cases of shorted lines. If two lines are shorted, the measured distance will be 0 ohm. 0 ohm is also measured when one of the lines is shorted to the body. In this case, the main line resistance in the other buses will measure 60 ohm. So, what will be the CAN bus resistance when one line is shorted to the body? That's right, 60 ohm. We just discussed that the terminating resistance of the CAN bus is 60 ohm when the bus is in the normal state. This means the resistance value is the same when one line is shorted to the body. This can be a little confusing. When the circuit is normal, the resistance at one of the bus lines and the body measures as infinite. If there is a short circuit, the resistance between the normal line and the body is 60 ohm. The resistance between the shorted line and the body is 0 ohm. We have learned about network and diagnosing the CAN communication based on the resistance value. Vehicle network resembles our nervous system. It allows us to realize the technologies we had imagined in cars. We hope you find this session useful to your work in the field and your continuous journey to build knowledge and experience. Thank you. Review what you learned from this session with quick quizzes. Remember, the best way to retain knowledge is to remind of what you learn while it is still fresh. Thank you for joining and completing the CAN communication session.